Example letter B, we have another separable equation. How do we know this is a separable equation? Because we have the product of a function of x times another function that depends only on y separately, so we don't have additions of the two variables really. All right, well, so here actually we're ready to separate the variables. So just like you solve any equation, any numerical equation, have the variables on the left-hand side and the constants on the right-hand side. Well, in this case, we want everything related to the dependent variable, which in this case is y, on the left, and everything for the independent variable on the right. So in this case, I think it just works very nicely to do cross multiplication. The dy and the dx over here and the y with the dy. So that's going to leave us with y dy dx, oh wait, no, that's just y dy equals to x squared over 1 plus x cubed dx. And we just separated the variables. All right, so we're ready to do the reverse operation, which in this case is to integrate both sides. All right. We're good to go and integrate. And, well, the integral on the left-hand side of the equation, that's just the integral of y, which is y squared over 2 on the one hand, right? And for the right-hand side, what about it? How would you value the integral on the right-hand side? U sub, right? I mean, let me set up that U substitution. So u equals 1 plus x cubed. Du equals 3x squared dx. Okay. Well, there's many ways to show the u substitution. So I think there's like 3 or 4 methods. Sometimes one of the methods is to solve for x squared dx and then substitute whatever you were left with. That's one. That's like solving an equation. I use the make a wish come true approach. What is that? Well, you wish you had 3x cubed here, 3x squared. Well, I need a 3, right? Provided you do the reverse operation, divide one out, all right? So multiply by the reciprocal outside, because what are we really doing? 3 times a third equals to 1, so we're just multiplying by 1, a very convenient version of 1 that satisfies our needs here, right? So this is the same as saying 1/3 integral of du over u, y squared over 2 equals 1/3 ln of absolute value of 1, or absolute value of u, right? Plus c. And again, last time we also discussed that we only add the constant of integration only to the right-hand side of the equation, right? Not on both sides. I showed you how, all right? Okay, so what's next? So back substitute y squared over 2 equals to 1/3 ln of, in this case, I need to keep the absolute value bars. In some cases, you don't need them. Y, in some cases, we need them. Y, in some other cases, we don't need them because we don't know what x is here, right? So x can be positive or negative, and in some cases, a negative number cubed, especially a really big number cubed, negative cubed, that's going to give us a really big number negative, plus 1 is still going to be a negative, so we need the absolute value bars to fix that problem over there, the domain, a domain problem. If the result were something like 1 plus x squared or 1 plus x to the 4th, well, raising to an even power, we don't need absolute value bars. You can keep them anyway, but they're not necessary. All right, so here is the thing with this special kind of equation. So number 1, well, let me multiply both sides by, by 2. Okay, 2. That's to isolate the y, all right? And that's y squared equals to, 2/3 ln of absolute value of 1 plus x cubed. Plus, what is 2 times c? That is a constant we don't know about times any number. It's the same constant. Again, by absorption, we just do time plus c, right? We don't keep the coefficient. Now, here is where things get a little tricky. And I'm talking about one of the homework questions, by the way. one of the homework questions, the way it's worded, it's asking to obtain the largest solution and the smallest solution. Why is that? Because what happens if we solve for y right here? We need to take the square root on both sides, right? However, because the exponent is even, like a square root, like a 4 root, we need that plus minus, right? So that's y equals to plus or minus square root 2/3 ln absolute value 1 plus x cubed plus c. Okay, that'll be the solution, all right? And well, that's technically not a function because we're getting two different outputs for the same input. However, I'm going to break this up into y equals, or y1 if you will, negative square root of 2/3 ln of absolute value of 1 plus x cubed plus c, and y2 equals to square root 2/3 ln absolute value of 1 plus x cubed, all plus c. So what do each solution represent? Well, the solution with the negative sign will represent the smallest solution, and the solution with the positive sign will represent the largest solution. All right? Just so when you look at the homework, when you get these kind of solutions, and when you look at this wording of problems, you don't freak out like, hey, what does it mean by the largest or the smallest solution? Okay. I mean, let's do another example. The next one, along with a particular, or with an initial condition. So, what have we gotten here, by the way? For examples, letters A and B, because the solution still contains the concept of integration. Again, this is really the portrait of a family of functions given. So that's why we call this the general solution. So, example letter C. Notice the equation goes along with a condition. So this time, after solving the equation, we're going to look for the particular solution, the particular member of the family of solutions that contains the point 0, 5. All right? Okay, so let's go for it. So let's ignore that condition for a while. And let's see. So this is, okay, number one, I would change the derivative symbol to Leibniz notation, that is dy dx. Okay? And at the same time, I'm going to factor x from the right-hand side. With this, we actually show the equation is separable because what do we have? A function of x times a function of y, so we're good. So let's separate the variables. So that'll be dy over 1 minus y equals x dx. All right? So what about the integral on the left-hand side of the equation? Any ideas? ln? Yeah, there's an ln, but actually we don't need, for one like this, you may not need to show all the setup because, well, I know there should be a negative sign to compensate. However, what I'm going to do, I will factor out the negative sign, dy over y minus 1 equals x dx. This way we can integrate immediately without even showing. I mean, for something like what we have on the left-hand side, don't bother showing the UDU. I think it's obvious, right, that it's going to be simply ln. Because, I mean, there's no wish we need come through, right? There's a 1 in the dy, all right? So that'll be negative ln of absolute value of y minus 1 equals x squared over 2 plus c, all right? Okay, so the next few steps may seem a little weird because of all the absorption processes we're going to go through. Yes, in the end, I'm going to show you like a summary of what we did, but let's get a little technical here. So number one, so we want to isolate y, right? Well, let's get rid of the ln, but we need to get rid of the negative. Divide both sides by -1, okay? So that's going to leave us with ln of absolute value of y minus 1. Well, while the -1 affects the x squared over 2, okay, it doesn't affect the constant of integration because that's just any number that we have no idea what it is. So by absorption, this remains plus c simply, all right? Now, we need to get rid of the logarithm. What do we do to get rid of a logarithm? Exponentiate both sides on the base e. All right? Cancel e with ln. All right. Also, let's recall that whenever we have a to the m plus n, that equals a to the m times a to the n. All right? That's just a basic law of exponents from algebra. All right? However, we're going to use this backwards. Number one, okay, keep the absolute value bar, right? And that equals e to the negative x squared over 2 times e to the c, okay? So the e to the negative x squared over 2, just leave it alone. What about e to a number that we don't know what it is? That's just another number that we don't know what it is. That's just c, all right? I'm going to call it like this, c, okay? So that's c, e to the negative x squared, okay? Oh, I need more space. C e to the negative x squared over 2, all right? Equals absolute value of y minus 1. Okay, here's the thing. How do we get rid of an absolute value? Remember when you guys solve an equation like this, absolute value of x minus 1 equals to 3. How do you solve that equation? Yes.
Would you have like two different versions of it?
All right. Or in a compact form, x minus 1 equals plus or minus 3, right? And then you would split it in two equations. So that's what I'm going to do here, okay? So let me get rid of this and let me get rid of that as well. So I'm going to need the space for the initial condition. Let me continue up here, I guess, okay? So that's going to take us to y minus 1 equals to plus minus c e to the negative x squared over 2, all right? But I mean, plus minus c, what is that equal to? By absorption, it's still equal to just c, all right? And simply add 1 to both sides. That's 1 plus c e to the negative x squared over 2, all right? And that is our general solution. All right, that's our general solution. Well, so I know, guys, I could have simply gone from this step, we can possibly see, to here. But I wanted to explain everything behind the absorption of the constants, bring back those memories from absolute value functions and equations, how do they work, and I mean in the end that plus or minus that came out of eliminating this absolute value just goes away because it's multiplying by a constant that we don't know what it is. Okay, so that's just the general solution with y of 0 equals to 5, which means when x equals to 0, y equals to 5, substitute into the equation in order to get the particular solution. That is the value for c. So let's go about it. So that is y equals to 5 equals to 1 plus c, which is simply c e to the negative 0 squared over 2, which is 5 equals to 1 plus c. What is e to the 0 over 2 quantity squared? Yeah, that's still simply e to the 0, which equals to 1. And this is 5 equals 1 plus c times 1, which is just c, and c equals to 4. So that is the constant of integration here, right? Now we need to go back to our general solution and write our particular solution. Y equals 1 plus 4e to the negative x squared over 2. Final answer. All right. Oh, let me label this as a particular solution. Again, with c's general, without the c's particular. All right. So let's see what's next. Yes, applications, growth and decay. Well, these applications actually are going to look exactly what you did in pre-calculus or college algebra math 101. And even in calculus 2, when you get to solve differential equations, you get a little bit into growth and decay. However, in pre-calculus or in college algebra, they just tell you to memorize an exponential function that describes this growth or decay. Here, with differential equations, we're going to see where is that formula come from, where is that function coming from. Well, so the very simplistic population growth model tells us that the rate of change of some population size with respect to time is proportional to time. Of course, we are not considering many other factors, like there's other models like limited growth, which considers limited supplies. Of course, that's a more suitable model to if we were to work realistically, right? But well, we're just going to look at this baby method, right? So if we solve this equation, so that's dy equals kt dt, integrate both sides, so that equals y equals to, wait, no, what am I doing here? This was not supposed to be t. There's a little typo here, guys. It's supposed to be y. So it's, yeah, because I was supposed to say that it was proportional to its size, not time. So that actually goes dy over y equals k dt. Okay, there's a little typo. Sorry about that. Integrating both sides, that gives us ln of absolute value of y equals kt plus some constant of integration. All right, well, let's solve for y right here. So e on both sides, and that equals absolute value of y equals to e to the kt times e to the c, which again is just another number, right? Very similar to what we did in the previous example. And I'm going to skip the absolute value, the plus and minus. We already explained that. So at this point, I will do that. So y will be simply c e to the kt. Remember this formula you were asked to memorize back in pre-calculus? They told you, oh, the initial population is whatever 1,000 people or fish, depending on the situation. And again, how do we know this model describes decay or growth? It's going to be given by the sign of the exponential. Positive exponential gives us an increasing function, of course. That means growth. And negative exponential, that means decreasing function or decay. All right? So let's have a look at one example. All right? Okay. So what do we have for this first application? So the rate at which a population is growing is directly proportional to its size, not time, to its size. Okay? The population was 100,000 people at the end of 2000 and 120,000 people at the end of 2010. Write a function p of t to represent the population at any time where t equals to 0 corresponds to the end of 2000. So that's our initial time. All right. Okay. So this is what we're going to do. So we're going to use the first. So t equals 0, which corresponds to 2000. So that's telling us that that the initial population, which is when t equals 0, that equals the population, or y, equals to 100,000 people. All right. So I'm going to use this condition or these two pieces of information, and that's going to be helpful to get the c. So number one, this will be p equals to c e to the kt. So I'm going to substitute population. Let me call this p instead of y. Then 100,000. I mean, not 10. C e to the k times 0. Well, k times 0 equals to 0. E to the 0 equals to 1. That means c equals to 100,000. All right? So we may go ahead and write, actually, this function, p of t equals to 100,000 e to the kt. Okay? All right, so now that we have our concept of integration, essentially, we're going to use the second piece of information. That is, at the end, in 2010, at the end of 2010, we had 120,000 people. That is, when t equals, well, that's supposed to be 10 years after, right? So when t equals to 10, the population size was 120,000. So that's to get the constant of integration. The rate constant, all right, or the constant or the growth constant. So 120,000 equal 100,000 e to the k times, what's that? 10. Okay. And, well, let's divide both sides by 100,000. Okay, so cancel. And I'm going to cancel a few zeros here. 12 over 10. I'm just going to keep it 12 over 10. Okay, so that is 12 over 10 equals to e to the 10k. So let's solve this baby exponential equation for k to get the constant of growth, okay, or the growth constant. So I'm going to take ln on both sides for this. Take ln, and this is 10k equals to ln of 12 over 10. You might want to reduce it, maybe not, that's fine. Oh, be careful. Oh no, that's fine. Okay. So, k equals ln of 12 over 10. This is for the whole argument divided by 10. So that is our constant of integration. Our growth constant. All right. Okay, so wait, do I have an extra 10? No, that's fine, right? That's fine. Okay. So we can go ahead and write our function p of t equals to what is that? 100,000 e to the ln of, okay, I'm going to reduce 6 over 5. How about that? 6 over 5 t over 10. So that's going to be our function for this situation, right? So that's the model for any year. So that's the model we can use to predict the population size after t years, after 17 years, after 23 years, whatever, all right? So we have a model right now. All right, well, that's actually part B of the question. So, find the expected population by the end of 2025. Okay, so that is evaluate. Um, Again, we don't have to be careful when it comes to this type of problems where we are given the explicit years, the actual years. We don't substitute the big number because they're telling us to call zero for whatever the initial year they're telling us and just count them how many years from there. In this case, well, it starts from 2000, that's our zero, our natural zero for the situation, to 2025, simply substitute for 25. And I don't think I have the result for this one, so please help me out with the calculators. E to the ln of 6 over 5 times 25 over 10. Be careful when typing that logarithm, close parentheses for the 6 over 5. Okay, so this is approximately 157,744 people. All right, so that's, and yeah, we round to the next integer, of course, because it's people. All right. Okay, what's next? The next topic, which is our next application, it's on the next page. Newton's law of cooling. So, what is this about? So, for instance, think of a pizza, for instance, out of an oven. What's going to happen when you take it out of an oven? It's going to cool down, right? At room temperature. So, by nature, it's the cold object or the cold environment what cools down the hot object, not the other way around. That's why the pizzas get cold or get cooled down. All right. Well, so Newton's law of cooling, it tells us that the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Sometimes they call it ambient. All right. And well, the differential equation is dt. Yes, be careful because they're both t's. One of them is uppercase T for temperature. The other lowercase t is for time. Equals k times t minus t subscript m, where t subscript m is the temperature of the medium. All right. So, okay. So let's. The solution to this well, actually, I'm going to solve the equation right here. I'm going to take a different approach for this example. So, example number 3. What do we have? A cup of coffee with a temperature of 100 degrees is placed in a room with air temperature which is 60 degrees, which is, well, we're going to assume this is a constant temperature, right? If the coffee cools down from 100 degrees to 90 degrees in 5 minutes, how much longer would it take for its temperature to decrease to 80 degrees? And that's something you can try at home. You can warm up a coffee, check the temperature of the surroundings, or get a thermometer and put it on a pizza slice. I don't know. You can try it and you can do the experiment at home. Should work. All right. Okay, so what do we have here? So number 1, dt, the t, I know it's different t's, right? Okay, that equals k times whatever temperature of the object, because in this case, the temperature of the object is the one that changes. That's the variable here. I didn't substitute anything for uppercase t. However, I'm going to substitute T subscript m for the temperature of the medium, which in this case is 60 degrees. All right? So again, we are assuming the temperature of the environment, of the medium, it's actually constant. If it's not constant, then we should write a whole different differential equation. That gets a problem more complicated. All right? Well, so I think this is a nice and easy separable equation. dt over t minus 60 equals k times dt, integrating both sides, that's ln, absolute value of t minus 60, equals KT. All right, plus some constant of integration, of course. All right. Let's take the natural log on both sides again. So taking the log on both sides, we exponentiate on both sides to get it. So that's absolute value of t minus 60 equals e to the kt. And at this point, hopefully, well, no, actually, I'm going to do the whole thing, e to the c. And then I'm going to do one step at a time. So absolute value of t minus 60. I don't want to make things obvious or something. E to the kt. And however, well, in this case, I'm just going to take the absolute values. I'm going to cheat a little bit here, right? And simply go in t minus 60 and skip the plus minus and the absorption, all right? C e to the kt, all right? So that's finally t equals to 60 minus c e to the kt. Question for you. How many of you got to this topic in pre-calculus or college algebra? You see this before, some of you? It's typically an optional topic. It's not a topic we are supposed to cover. So that's only like if time permits, you know? I mean, the rest of the problem should be mechanically similar to what we just did, right? So, question? I don't know. Plus. Yeah, thank you. That was supposed to be a plus. Thank you. So, I think I was looking at this minus, maybe. Okay. So, let's write the information given in words into function notation, into condition notation. Well, so the cup of coffee is at 100 degrees, right? So that means that's the initial temperature of the coffee. As soon as you finish brewing your coffee, take the temperature. That's 100 degrees. So that means T of 0 equals to 100. We're going to use this initial condition to, guess what? Find the value of C, just like we did with the previous example with the population. So that is T equals to 60 plus, 100 equals to 60 plus C e to the k times 0. All right? K times 0 again, that's equal to 0. E to the 0, it's still equal to 1. 1 times C equals to C. C plus 60 equals to 100. I'm just reversing the order of the equation. And then subtract 60 from both sides. That is, C equals to 100 minus 60. All right? Which is C equals to 40. All right? That is, go back to the function to write T of T equals 60 plus 40 e to the kt. In fact, guys, maybe the formula you got to see back in pre-calculus or college algebra was simply this one. T of T equals to temperature of the medium plus temperature minus temperature of the medium e to the kt. That's the formula they gave you and potentially asked you to memorize. But in this exercise, we're trying to set up the problem by means of a differential equation. So we can practice the method of separation of variables. That's the first half of the problem. The second half of the problem is just back to pre-calculus. As you can see, it's the same process. Really nothing new here. All right. So now we're going to use the second condition. All right. That is, okay, let me highlight that. Okay, so it takes 5 minutes, okay, to go from 100 to 90 degrees, or no, wait, to decrease, for 90 degrees, okay? So we're going to use this condition now to find the, well, in this case, well, I don't want to spoil things, okay? So this will be, so we're going to write with this information I highlighted, I'm going to write T of 5 equals to 90. Because that's what it takes for the coffee to cool down from 100 degrees to 90 degrees. So with T of 5 equals to 90. So I'm going to go back to this model here. So 90 equals to 60 plus 40 e to the k t, well, e to the k times 5. And let's solve another exponential equation. So let's subtract 60 on both sides. I'm going to go ahead and write 40 e to the 5k equals 30. Okay, equals to 30. And I'm going to divide both sides by 40, that's e to the 5k, equals to, how about 3/4? Okay, 3/4. Let me make this look like a 3. There we go. And to isolate, to get rid of the exponential, take ln on both sides. And you can leave it as 3/4, or you can take the ln of 0.75. It doesn't matter. That for this case, it's a nice fraction to go with. So I don't know, it doesn't really matter that much. Okay, so that's 5k equals ln of 3/4, and k equals to 1/5 ln of 3/4. So now we have a complete model, right? So in summary, if you want to try this at home, you need to take two pieces of information. The one exactly at the beginning, if you're doing it with a pizza, as soon as you take it out of the oven with the thermometer, and then however long you want to do for the second condition, 10 minutes, 5 minutes, that's up to you, all right? And with this, we get the entire model, the complete model. T of t equals to 60 plus 40 e to the k, which is 1/5 ln of 3/4 t. Back in pre-calculus or in college algebra, you used to just put decimals in the exponent. In this case, I'm leaving everything in exact form because, again, just like in chemistry and physics, we are not supposed to round anything until the very end because we can get into issues with the accuracy, the significant figures, and all that depending on the situation. So T of t equals to 60 plus, oh wait. So that's the model, right? That's the model. Now we can answer the question. Now the question is, okay, let me go back to the top. How much longer will it take for its temperature to decrease to 80 degrees? All right? So all we do is, so when will it be 80 degrees? Okay, so we substitute 80 equals to in the temperature, and then that's 60 plus 40 e to the 1/5 ln of 3/4 t. Okay. Oh, but I'm not substituting anything for t because that's a question, right? You're asking is when. Okay, so let's subtract 60. That's actually 40. First of all, 40 e to the 1/5 ln of 3/4 t equals to 20, and dividing both sides by 40, so that's e to the 1/5 ln of 3/4 t equals to 20/40. Isn't that a half? Right? Or 0.5, either way. That's 1/2. And guess what? We're going to take ln 1 second time. All right, we'll take ln 1 second time. And notice we're keeping everything in exact form. We are not really getting anything approximate until the very end. So this is 1/5 ln 3/4 t equals ln of 1/2. And well, all we need to solve is to solve this linear equation. Yes, it's linear despite the ln. The ln is just a constant. It's a slope of that linear on the left-hand side. So t will be exactly 1/2 ln of 1/2 over 1/5 ln of 3/4. So that will be the exact answer. But of course, we're not going to report final answers like this because each time we want to have a sense of a more numerical a more numerical sense, right? Okay, so this is approximately 12.047, which is simply this is simply 12 minutes. I mean, let's round it to 12 minutes, right? 12 minutes. Okay, but the question, be careful. They're asking us how much more longer, not how long does it take. Because it already, so it takes, okay? They're telling us it takes 5 minutes, right? To cool down to 90 degrees. To go to 80 degrees, if it takes 12 minutes, if 5 have already passed, we need 7 more minutes. Be careful on the wording of the question, right? All right. What else do we have? Oh, yes, the next problem, I believe it's the mixing problem. Okay. Okay, so mixing problems. A very classical application in differential equations is when we're mixing solutions where we have a solute of different concentration. But we want to mix them together to obtain a different concentration, or maybe you are in the craft beer industry and you have different beers, you want to come up with a mixture of them having a certain percentage of alcohol, or in the wine industry, for instance, you want to mix different harvests, different ages of wine which have different alcohol levels, like a Cabernet, like a Merlot, different. You want to mix them together to get a particular concentration for the new product you want to release to the market, right? Well, you need differential equations for this, all right? And well, what is it? So a typical mixing problem involves a tank of fixed capacity. So that's a given, all right? Containing a thoroughly mixed solution of some substance, such as salt, sugar, alcohol. A solution of a given concentration enters the tank at a fixed rate, and the mixer, which is thoroughly stirred, leaves at a fixed rate, which may differ from the entering rate. In some cases, it's the same rate. In some cases, the rate is different. So if it goes out faster, actually the container is going to lower in its volume, right? And actually, that's going to give rise to a linear first order equation, which is what we're going to do in the next couple of sections. So we're going to do the first case, the case in which we have the same rate coming in and coming out. All right, that is the volume inside of the tank will remain constant. Okay, the volume, the amount of liquid, that's what I'm trying to say. So let's see. A tank contains 100 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains at the same rate. The question is how much salt is at the tank after 10 minutes. So what we're going to do is we're going to come up with a model to find out the concentration or the amount of salt after your favorite time. Or you can use this model to, what if you want to release, what if you want to come up with a solution that has a particular concentration? Then you would solve an equation for T because you want a particular concentration. Well, number one, a picture will help, okay? So what do we have? The big container. And what do we have? Okay. Coming into the tank, okay, we just have water at a rate of 10 liters per minute, okay? 10 liters per minute. Okay, so what do we have inside of the container? Inside of the container, we have the entire, everything, the 10,000 liters with 15 kilograms of dissolved salt. All right, so that means here inside of the container, inside of the tank, we have 15 kilograms of salt. Okay, what do we have going outside of the tank? Okay, so here we have a mixture, water, salt. All right, that's a brine solution. And it's actually, we have the case in which the flow out is exactly the same. 10 liters per minute. All right? So, how are we going to set up this differential equation? Okay, so number one, we have the model at the top. So the rate of change of the amount of that solid per unit of time will be the difference between rate in minus rate out. Why do we have rate in minus rate out? Why not the other way around? Because, well, the reference is the container, the tank. Whatever comes in is positive. Whatever comes out, it's what we lose, right? It's what we let go. So that's why it's negative. So dA dt equals to rate in minus rate out. How do we calculate each of them? So rate in is the product between flow in rate times the concentration of that solute in that it's coming into, minus flow out rate, which in this case for both they're the same, times the concentration of what is coming out. All right, here's the thing. Number one, flowing rate. Flow in times concentration in minus flow out rate times the concentration out, right? And that equals dA dt. Okay, flowing rate. We're given that flowing rate and flow out rate are both the same, right? 10 liters per minute. So, dA dt, that's 10, okay, times the question here is, what is the concentration of salt coming in? It's just water coming in, right? So whatever concentration, and here is where the chemistry comes into play. It could be a concentration expressed as percentage, or as a percent volume, as a percent mass, or molar, normal, the different units to express concentration in chemistry. All right? Well, in this case, that's 10 times nothing, times 0, because there's no salt coming in, just water. Minus, what is the flow out rate? Well, they're telling us it's exactly the same, 10. And, well, what about the concentration out? Here's where it gets a little tricky. The concentration out will be variable because depending on how much water comes in, we have 15 kilograms of salt. More water coming in, brine coming out. So the concentration of salt is going to decrease as time moves on, right? So, but we don't know. How do we express this? Well, we're going to express this as a percent or as a ratio solute per volume, okay? In this case, I'm just going to call A, which is the amount of salt, divided by the total volume. But what's the total volume in this case? 1,000, right? That's 1,000. Okay, so we're ready to simplify. So we got the hardest part of the problem, setting up the equation. Let's simplify. So this is going to go to 0, of course. dA dt equals to, what is that? 10 over 1,000. That's 100. Negative A over 100. Okay? And we're ready to solve this differential equation. All right? And this is a separable equation. The A can go dividing the dA, the dt go multiplying with the negative 1 over 100. So, let me continue here, okay? So, that's dA over A equals negative K, which K? No, that's negative 100 dt, all right? And we can easily integrate this one, both sides. The integral of dA over A, what would that be? Natural log of absolute value of A? Okay? However, guys, I'm just going to go and say ln of A because are there any negative amounts of salt? It's either 0 or positive, so I think the absolute value bars are relevant for the situation, for the context of the situation. So this is equal to -1/100 t plus c. So that is the general solution to the equation. Yes, yeah, we're going to do the exponentiation soon. However, I think I'd rather use the initial condition to get a particular solution so we can get the model the way it is. Now, how do we get the initial condition? It may not be clearly stated, right? It's kind of cryptic here. So, in the end, what are we talking about? What changes? Isn't that the amount of salt? So, how much salt is at the very beginning?
15.
Okay, so this means A of 0 equals 15 because initially there are 15 kilograms of salt. All right. Okay, so that's ln of 15 equals to -1/100 times 0 plus c. So c equals ln of 15. All right. Okay, so we're good to go. Go back to the differential equation. And so this is ln of A equals -1/100 t plus ln of 15. Okay? So that is the particular solution, except that it is in implicit form, because I still have that natural log operator on the dependent variable, which is the amount of salt in this case. All right, so let's exponentiate both sides. I mean, I could have done the exponentiation from here, but by leaving the equation in terms of logarithm, we save time because I would have had to do another exponentiation and then another logarithm. So why do and undo many times? So this is E. Okay. And A equals to e to the negative t over 100 times e to the ln of 15, all right? Which is a of t, that's finally the model we need. E to the ln, that's 15, e to the negative t over 100. Let's assess our result. How does that make sense? So here, I mean, naturally, because we're mixing a solution that it's already 15 kilograms per 1,000 liters of water, we're getting water into the tank, and then a new solution is getting out of the tank. However, that solution will be more dilute as time progresses, right? So that's explained by the negative sign because we have a decay, we have a case of decay. So that's a good way to assess our results here. All right. So let's see.